Hey everyone, welcome. If you're gearing up for that big computer science exam, you are in the exact right place. In today's explainer, we're going to completely demystify binary arithmetic. We are setting a really enthusiastic, laser-focused tone today to help you absolutely master binary addition, subtraction, carries, and oh yeah, those notoriously tricky chained borrows. Seriously, by the end of this, you're going to walk into that exam room with absolute confidence. Let's do this. So here is our roadmap for the masterclass. We'll start with addition rules and carries, look out for the overflow trap, break down subtraction and borrowing logic, dive into the twos complements method, and finish up with some actual exam practice to really test your skills. All right, let's jump right into part one, the rules of binary addition and the carry. Okay, let's review the 4 core rules. The first 2, super easy. They're identical to the regular decimal math we do every day. 0 plus 0 is 0, and 0 plus 1 is 1. Easy, right? But here is the exact spot where students trip up, 1 plus 1. In our standard base 10 world, that's 2. But remember, there is literally no number 2 in binary. So 1 plus 1 actually equals 0, and you carry a 1 into the next column to the left. Why? Well, because a 1 in that next column mathematically represents a 2. And hey, if you ever run into 1 plus 1 plus 1, the result is 1, and you carry a 1. Definitely keep these locked in your memory. Now, this perfectly illustrates the visual column layout you should always sketch out on your exam. Notice our 8-bit number line up top, doubling from right to left, 1, 2, 4, 8, all the way up to 128. We are adding 85 and 170 here. Just follow the values in the middle rows, going right to left. 1 plus 0 is 1. 0 plus 1 is 1. And it just flows perfectly all the way down the line. We didn't even need to use a carry row for this one. The result at the bottom gives us 8 straight 1s. If you add up those column values, 128 plus 64 plus 32, and so on, it perfectly equals 255, a really nice clean start. Moving right along to part 2, the binary overflow trap. Let's crank up the difficulty a bit and add 95 and 222. As we process this right to left, we're generating carry values almost immediately. Check out the 32 column. We've got a 1, and a carried 1. That drops a 1 at the bottom, and we carry a 1 to the 64 column. But follow that chain reaction all the way to the far left edge. At the 128 column, we're adding 0, 1, and our carried 1. That drops a 0, but wait, we have to carry a 1 again. Look at that final carry falling straight off the left edge into a non-existent 256 column. We've literally run out of space. So what's happening there? That falling digit is what we call binary overflow. It's a massive warning sign. It happens when the sum of 2 numbers exceeds your fixed bit storage capacity. An 8-bit register can only hold numbers up to 255, but 95 plus 222, that's 317. Because our final carrying 1 is just lost to the void, our remaining answer equates to just 61, which is completely, utterly incorrect. The result is mathematically meaningless. If you catch this happening on a test, write down clearly that an overflow error has occurred. All right, let's pivot to part 3, subtraction and borrowing logic. This is where things usually get a little tangled, so notice this side-by-side comparison. Think about normal, everyday decimal math. When you don't have enough to subtract, you just borrow a 1 from the next column to the left, right? And that borrowed 1 magically gives you 10 units in your current column because, well, it's a base 10 system. But in binary, which is base 2, when you cross out a 1 in the column to the left, you are actually bringing over 2 1s to your current column. Actually, if you remember nothing else about subtraction today, remember this quote. When you cross out a 1 to borrow, it becomes 2 1s in the column to the right. Think of it like breaking a $2 bill into 2 $1 bills. It makes so much sense, right? The column to the left is always worth exactly double the column you're currently in. So borrowing 1 unit from the left always yields exactly 2 units on the right. If you can visualize bringing those 2 1s over, binary subtraction becomes incredibly easy. So how do we handle chained borrowing, where you have to skip across a bunch of zeros just to find a 1? It's like a relay race. Step 1, cross out the nearest 1 to the left, turning it into a 0. Step 2, that 1 moves right, becoming 2 1s. Step 3, now this is absolutely crucial. If you have to keep moving those 1s further down the line to the right across 0 columns, you leave one of those 1s behind in the intermediate column and carry the other one forward, which then splits into 2 1s in the next column. Okay. Part 4, the twos complement method. What if I told you that you could sometimes completely avoid subtraction? If you need to calculate a minus b, you can just convert b into its negative form and add them together instead. To turn any binary number negative, we use this awesome, foolproof 3-step shortcut called 2's complement. Step 1, start at the far rightmost bit. Step 2, copy every single digit exactly as it is, up to and including the very first one you run into. Step 3, for all the remaining digits to the left, just flip them. Zeros become ones and ones become zeros. The whole shebang. That's it. You've instantly created the negative version of the number. Which brings us to part 5, exam practice. Time to really test yourself. All right, challenge number 1. This is a 3-row addition problem. I want you to convert the decimal values 76, 17, and 103 into 8-bit binary, stack them up, and add them together. Pause the explainer right here and solve it. Okay, let's see how you did. Check your work against this result. Did you get 1100100 at the bottom? If you got a little stuck, take a look at the 4's column. We add a 1, a 0, a 1, and a carried 1 from the previous column. We were adding 1 plus 1 plus 1. Following our rules, that drops a 1 at the bottom and carries a 1 to the next column. And the total beautifully matches the decimal value of 196. Great job on that one. Ready for round 2? This one is going to test your chained borrowing logic. Subtract binary 0010, which is decimal 2, from binary 1001, which is decimal 9. You're going to have to borrow across those zeros. Pause here and go for it. Let's break this one down. In the second column from the right, we needed to subtract 1 from 0. Obviously, we can't do that. So we had to go all the way over to the 8 column on the far left to find a 1 to borrow. We crossed it out, leaving a 0. It moved to the 4 column as 2 1s. But hey, we still needed a 1 over in the 2 column. So we took one of those 1s, leaving a single 1 behind in the 4 column, and brought the other over to the 2 column where it's split into 2 1s. Then 2 minus 1 is 1. The final result is 0111, which equals exactly 7. All right, the final challenge, the final boss, if you will. This tests the highest difficulty question type, 2's complement subtraction. I want you to perform 73 minus 106. But you must do this by first converting positive 106 into negative 106 using our flipping shortcut, and then adding them together. Pause here and solve. Let's look at the ultimate masterclass breakdown for this. Check out the conversion first. We took 106. Starting from the right, we copied the 0 in the first 1. Then we just flipped every single bit to the left of that. This instantly gave us negative 106, which is 10101110. See that leading 1 on the far left? That is our sign bit, letting us know for sure it's a negative number representing minus 128. Then we just added 73 to our new negative 106 using standard addition rules. The result, 1101111. If you map that back to the number line, minus 128 plus all the remaining positive bits perfectly equals minus 33. Before we officially wrap up, I want to give you a massive exam tip. Take a mental screenshot of this. Whenever you have time left over at the end of a test, always double-check your binary answers by converting them back to decimal integers. It's exactly what we did in all our practice rounds today. It's literally a built-in checking mechanism. If the decimal numbers don't add up, you know right away you need to trace your carries or borrows again. And wow, just like that, we're at the end of the explainer. You've systematically mastered the addition rules, the mechanics of carries, that super tricky chain borrowing across zeros, and the absolute genius of the 2's complement method. You even know exactly how to spot an overflow trap. So look at this final question. Are you ready to completely ace your binary arithmetic exam? Yeah, I think you know the answer. Take these visual layouts, use that $2 bill borrowing analogy, write out your number lines, and you are going to absolutely crush it. So what's stopping you from getting a perfect score? Get out there, keep practicing, and I'll catch you in the next explainer.